Welcome back. In this lecture, we will see the mathematical formulation for plane strain and plane stress. In the last lecture, we discussed how a given 3D problem can be idealized to a 2D cases, and we understood that it is plane strain, plane stress and axisymmetric condition. So, for a simple linear elastic isotropic case, we will see how the mathematical formulation of plane strain and plane stress would look like. So, we will start with the general linear elastic equations, where epsilon x is related to sigma x, sigma y and sigma z as given. So, epsilon x is equal to sigma x by E minus mu by E into sigma y plus sigma z. This is where we start with a typical linear elastic problem. Similarly, we have epsilon y, epsilon z, the engineering shear strain gamma xy, gamma yz and gamma zx. One can also represent gamma xy in terms of the pure shear strain or tensorial shear strain, which is given by epsilon xy. The relationship is, it is twice epsilon xy is equal to gamma xy. So, gamma xy is 2 epsilon xy. So, one can also replace this by this. In that case, you will have this particular side, it will change. So, gamma xy is 2 epsilon xy. So, then it will be epsilon xy is equal to tau xy by 2g. So, that is the difference. Okay. So, we will start with this. Now, for plane strain or plane stress. Now, in the case of plane strain case, the given condition is the strain is equal to 0. So, we need to have the inverse of this relationship as well, that is stress is in terms of strain. So, first let us, now this is strain in terms of stresses. So, we will try to find the inverse of this, that is stress as a function of strain. So, that is what we will do first. Now, we need to do some mathematical rearrangement and then find out what is the expression for sigma. So, we will start this. We need to obtain the equations of the form sigma is equal to E into epsilon. So, for that I strongly suggest all of you to follow these steps and work it out for yourself, because in this it may look a bit abstract. So, when we discuss the whole formulation, then it will be easy for you, but I strongly suggest all of you work it out on your own. So, first what I would like to do is I will try to eliminate one of these stresses. So, one of these stresses gets eliminated. For that, what are the different steps to be followed? The first step is multiply equation A by mu. So, you will have mu into epsilon x, mu sigma x by E minus mu square by E sigma y plus sigma z. Then do G plus B. So, this equation is G. Why should you do G plus B? In the process of doing G plus B, so this is G plus B, we will eliminate sigma x. So, that is the whole idea. In whatever manner you can eliminate, you can do that, but this is one particular step. So, G plus B will give mu epsilon x plus epsilon y is equal to mu sigma x by E minus mu square by E sigma y plus sigma z plus sigma y by E minus mu by E sigma x plus sigma z. Now, if you simplify this, the left hand side remaining same, you will get sigma y by E here minus mu sigma z by E minus mu square by E sigma y plus sigma z. So, in the process of this, we have got rid of sigma x. So, mu epsilon x plus epsilon y is equal to 1 minus mu square sigma y by E. If you combine these two, this one and this one, you will get this minus mu sigma z by E 1 plus mu. So, again if you rearrange this and this, you will get this expression. So, now you are left with two stresses. We need to eliminate again 1. So, call this as H. Then similarly you do G plus C. So, G plus C, once you do, you will get mu epsilon x plus epsilon z sigma z by E minus mu sigma y by E minus mu square by E sigma y plus sigma z, and rearranging you will get 1 minus mu square sigma z by E minus mu sigma y by E into 1 plus mu. You can see a lot of similarity between H and I. Now, it is very easy for us to again simplify this. Multiply H by 1 minus mu by mu. You multiply this particular equation by 1 minus mu by mu. So, we will be left with 1 minus mu, mu and mu get cancelled off. So, it will be epsilon x plus 1 minus mu by mu into epsilon y is equal to 1 minus mu square into 1 minus mu by mu into sigma y by E plus sigma z by E 1 minus mu square. Okay. So, mu again gets cancelled off from this particular expression. So, call this as J. Now, add I plus J, because you will have this is J, this is I, one of the stress will get again eliminated, that is why we have multiplied it by 1 minus mu by mu. So, once you do I plus J, we will get epsilon x plus 1 minus mu by mu epsilon y plus epsilon z is equal to 1 plus mu by mu into sigma y by E 1 minus mu the whole square minus mu square. Simplifying, we will get mu into epsilon x plus epsilon z. So, you can combine these two because this multiplied by mu. So, mu into epsilon x plus epsilon z plus 1 minus mu into epsilon y, same expression by mu. Here again you can do the simplification, 1 plus mu by mu sigma y by E. So, if you expand this, you will be left with 1 minus 2 mu. So, this mu and mu goes away. Finally, we will be left with the expression for sigma y. So, in the process sigma z also got eliminated. So, you can see that sigma y is equal to E upon 1 plus mu into 1 minus 2 mu into 1 minus mu epsilon y plus mu epsilon x plus epsilon z. Now, once you got the expression for sigma y, it is more or less the same for sigma x and sigma z. So, this is equation A. Similarly, you can write sigma x and sigma z, the expression which is A, B and C. So, this is the required form for applying the condition for plane strain. You can also do by after applying the condition for plane strain, you can simplify. So, we have done it before, so that it becomes very easy to just apply the condition for plane strain. So, you have linear elastic equations in terms of epsilon, that is strain, in terms of stresses, and now we have inverted this and we have got now stress in terms of strain. So, these are the equations. You can note that these remain same, E upon 1 plus mu into 1 minus 2 mu, and here it is 1 minus mu epsilon y plus mu into epsilon x plus epsilon z. So, now it is easy. We know for plane strain condition, strain in one direction is 0. So, epsilon z equal to 0, gamma x z, gamma y z is equal to 0. If we put this in the expression, we will get, that is, we are substituting in equations A, B, C, we will get sigma x is equal to E upon 1 plus mu 1 minus 2 mu, 1 minus mu epsilon x plus mu epsilon y, epsilon z goes away, sigma y and sigma z. So, sigma z, the expression is this. It is slightly different from the earlier one, because here the contribution of sigma z goes away. So, you are left with mu into E 1 plus mu 1 minus 2 mu into epsilon x plus epsilon y, and tau x y is equal to g into gamma x y. Earlier we have written gamma x y is equal to tau x y by g, or it is 2 into g into epsilon x y. You are replacing gamma x y by 2 epsilon xy. Now, one important point is, like, even though sigma z is equal to 0, sigma z is not equal to 0 for plane strain condition. So, these equations are known as the constitutive relationship for plane strain for linear isotropic elastic material. So, constitutive relationship, we know that is the relationship between stress and strain, and it represents the material characteristics as well. Here this is specific to plane strain condition. We have derived or we have formulated equation, the constitutive relationship for plane strain corresponding to a simple linear elastic isotropic material. So, we are just rearranging that, whatever expression that we got for plane strain in matrix form. So, you have sigma x, sigma y, tau xy, these are the three stresses which are present. Whatever we have got in the previous slide, we are just rearranging it, and you have E 1 minus mu, 1 plus mu, 1 minus 2 mu, E mu 1 plus mu into 1 minus 2 mu. So, these are symmetric, the other components are 0, and there is 2g corresponding to tau xy. In addition, we also know sigma z is equal to mu into sigma x plus sigma y. So, if you substitute this in the expression, you will get this particular value as well. So, sigma z is not an independent stress. So, if you just insist on this particular matrix, that is sufficient for solving the plane strain problem, because sigma z is again a function of sigma x and sigma y, it is not an independent stress. Hence, the above matrix formulation is sufficient for plane strain condition. Now, constitutive relationship for plane strain in terms of principal stresses. So, some more will go away. So, you have sigma 1 is equal to E upon 1 plus mu 1 minus 2 mu 1 minus mu epsilon 1 plus mu epsilon 3. What is the difference in earlier formulation and plane principal stresses? The shear stress component goes away, that is the only difference. Replace sigma x, sigma y, sigma z by sigma 1, sigma 2, sigma 3. So, here sigma 3 is equal to E upon 1 plus mu 1 minus 2 mu 1 minus mu epsilon 3 plus mu epsilon 1, and sigma 2 is mu E by 1 plus mu 1 minus 2 mu into epsilon 1 plus epsilon 3. And sigma 1 plus sigma 3, if you take sigma 1 plus sigma 3, you will be left with E by 1 plus mu 1 minus 2 mu epsilon 1 plus epsilon 3. Now, you please compare this equation with sigma 2, it is same. So, that is how you can very well replace sigma 2 equal to only this mu is additional here, remaining E 1 plus mu 1 minus 2 mu into epsilon 1 plus epsilon 3 is sigma 1 plus sigma 3. So, one can always write sigma 2 is equal to mu into sigma 1 plus sigma 3. Earlier we have written in the same kind of expression. So, it is similar to sigma z is equal to mu into sigma x plus sigma y. So, here in terms of principal stresses, one can write sigma 2 is equal to mu into sigma 1 plus sigma 3. So, constitutive relationship for plane strain in matrix form, one can write, this is exactly in terms of 2D, the effect of sigma 2 is not considered here. You can write sigma 1 sigma 3 E 1 plus mu 1 minus 2 mu 1 minus mu 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 1 minus mu epsilon 1 and epsilon 3. Here we have considered only 2 dimensional stresses. So, what we have done is the mathematical formulation for plane strain. Now, let us see for plane stress. For plane stress, it is the condition of one stress in one direction is 0. So, we will have to use the very first equation of strain in terms of stresses and substitute this particular condition. So, we will see how it will look like. So, you will have epsilon x is equal to 1 by E sigma x minus mu sigma y, epsilon y, epsilon z and gamma xy, which is equal to tau xy by g, or sigma gamma or gamma xy is equal to 2 into 1 plus mu tau xy by E, because you have replaced g by this expression. We have the expression E is equal to 2G into 1 plus mu So, by substituting that you have obtained in terms of E. So, here is a mere substitution of sigma z, tau z x, tau z y equal to 0. So, we are left with these equations. So, here also we have to note that even though sigma z is equal to 0, epsilon z is not equal to 0. We know this because we have the contribution of sigma x and sigma y in the other lateral direction. The strain, it will also influence the strain. So, hence epsilon z is not equal to 0. So, there are 4 strain components and 3 stress components altogether. So, strain tensor for plane stress is denoted in this particular manner, epsilon x, epsilon xy, and we have epsilon z as well. Stress equations for plane stress, by inverting the previous expression, we can get sigma x is equal to 1 minus mu square epsilon x E into mu 1 minus mu square epsilon y. We are doing the inversion, it is a simple rearrangement. So, one can always try this. You will get sigma x is equal to E by 1 minus mu square epsilon x E into mu 1 minus mu square epsilon y, and you have sigma y and tau x y. So, this is stress in terms of strain. So, to write the stress tensor, you will have E by 1 minus mu square, E mu 1 minus mu square into 0. So, E mu by 1 minus mu square. So, this is the expression for this is the matrix representation of stress for plane stress condition, and epsilon z is equal to minus mu by E sigma x plus sigma y. Substituting the expression for stresses, that is sigma x and sigma y, we have seen in the previous slide. If you substitute it, one can get epsilon z is equal to minus mu by 1 minus mu epsilon x plus epsilon y. So, in this lecture we have done the mathematical formulation for plane stress and plane strain condition. So, plane strain 2D idealization is more prominent in geomechanics than plane stress. Constitutive relationship for both plane strain and plane stress discussed for a simple case of linear elastic isotropic material. Plane strain has strain in one direction to be negligible, that is this particular expression epsilon z gamma x z gamma y z is equal to 0, and also even though epsilon z is equal to 0, sigma z is not equal to 0 in the plane strain condition. Similarly, we have even though sigma z is equal to 0, epsilon z not equal to 0 in the plane stress condition. So, this is all about the mathematical formulation of plane strain and plane stress. In the next lecture, we will see the mathematical formulation for again for the simple case with respect to axisymmetric condition. Thank you.